Preparation methods of carboxylic acids. We have seen different types of preparation methods like using Jones reagent, primary alcohols to carboxylic acids, aldehydes to carboxylic acids by Tollens or Fehling's reagent. We have seen esters, acid anhydrides, nitriles, amides, alkyl benzene, Grignard reagent by using dry ice. So we have seen the different methods in which you can prepare carboxylic acids. Now let us go into properties. Properties of carboxylic acids. Properties of carboxylic acids. Here we are going to discuss about physical and chemical properties. Now in this, first let us see physical. Physical properties. Now physical properties means basically we will discuss about the state of the compound, boiling points of the compound or solubility of the compound and so on. So let us see how they are. Carboxylic acids up to 9 carbons, acids that are containing up to 9 carbons, means methanoic acid, ethanoic acid, propanoic acid, up to 9 carbons, non-noic acid. Exist as liquids at room temperature. Okay, and these are colorless. They are colorless and they have unpleasant odor. Okay. Because they are volatile. They are also volatile. Similarly, higher carboxylic acids, are wax-like solids. They exist as wax-like solids. Okay, at room temperature. And they are non-volatile and also no odor because they are non-volatile. Similarly, carboxylic acids boiling points are higher than uh, higher than, or you can say greater than aldehydes, ketones, and even alcohols also. Alcohols also. Because of extensive hydrogen bonding means lot of hydrogen bonding between the molecules, and also intramolecular hydrogen bonding between the molecules, even in vapor phase, So there are so much intramolecular strong hydrogen bonding will be there that even vapor phase also they exist in diatomic dimolecular state, dimeric state. Okay, example, let us take this. Let us take acetic acid dimer. This is one molecule of acetic acid. This is the second molecule of acetic acid. Here the hydrogen bonding is present between them. Okay, so it is a existing dimeric state even in vapor phase. Dimeric state. So much of strong hydrogen bonds. That's why carboxylic acid's boiling points are greater than the respective aldehydes, ketones, and even alcohols also. Okay, so of comparable masses. Next, simple aliphatic carboxylic acids, up to 4 carbons. Means methanoic acid, ethanoic acid, propanoic acid, and butanoic acid are soluble in water. And as the number of carbons or the carbon chain increases, solubility decreases due to what will happen if carbon chains increases? Hydrophobic nature increases. Due to hydrophobic nature increases, because as the alkyl chains are more, automatically hydrophobicity or the hydrophobic nature increases, right? Benzoic acid is insoluble in cold water. Insoluble in cold water it is. Okay. So that is this aliphatic carboxylic acids, at least up to 4 carbons, they are soluble in water. As the number of carbon alkyl groups or carbon chain increases, hydrophobic character increases, so solubility decreases. Benzoic acid, first of all, it is insoluble in cold water. Other aromatic carboxylic acids are insoluble. Okay, and also these carboxylic acids, higher carboxylic acids, I can say, are also soluble in organic solvents, like ethanol, CCl4, okay, or chloroform, etc. Okay, so this is about the physical characters of carboxylic acids. Now next we'll see chemical characters. Now next let us see chemical properties of carboxylic acids. In chemical properties of carboxylic acids, we are going to broadly study about two types of reactions. Reactions involving OH bond cleavage and reactions involving complete OH, that is CO bond cleavage. Okay, what are those? Like similar to that of alcohols we have studied. Reactions involving OH bond cleavage and reactions involving CO bond cleavage. Similarly, here also we have classified them into two. Under that, first one, reactions involving OH bond cleavage. This one. Reactions involving OH bond cleavage. So OH bond cleavage is nothing but H plus. H plus is given out. Nothing but here we are studying about what? Acidic character. Okay, acidic reactions we are talking about. Okay. Now in that we are going to study about reaction with the metals and alkalis. Reaction with the metals and alkalis. So same here, electropositive metals can react with acids with the liberation of hydrogen gas. Same reactions. What are those? You take any carboxylic acid on reaction with sodium metal. Okay, what happens? Produces sodium carboxylates, right? Plus hydrogen liberation. Okay. Not only this, carboxylic acids can react with alkalis also or bases also. You take acid plus base, gives rise to RCOONA plus H2O plus H2O, salt plus water. It can also react with another mild this one alkalis like sodium bicarbonate. Okay, sodium bicarbonate also it can react. It forms sodium carboxylates with the liberation of carbon dioxide gas. Okay, so basically bases or with metals, the reaction can happen with the liberation of, if it is metals, liberation of hydrogen gas, if it is base, NaOH like that, water, and if it is slight bases, then it is, you can get carbon dioxide, means bicarbonates. If it is carbon dioxide is liberated out. So this is reaction with metals and alkalis. Next we will see so in the acidic nature, in the acidic character only, when any carboxylic acid is dissolved in the water, what will happen, sir? Basically, carboxylate ion is formed. Along with this ion, H3O plus or hydronium ion H plus is formed, right? Now, I would like to write the equilibrium constant K equilibrium for this reaction. Products concentration divided by reactants concentration by reactants concentration. You can also write this one as K equilibrium into concentration of water is equal to this term, that is RCO minus H3O plus concentration divided by RCOOH. That term is nothing but Ka. What is Ka? Acid dissociation constant. Okay, RCO minus concentration into H3O plus divided by RCOOH is what? It is nothing but acid dissociation constant. Acid dissociation constant. In the first year we have studied this in acids and bases lesson, chemical equilibrium. This is equilibrium constant. It is acid dissociation constant. As you know, higher the Ka value, stronger will be the acid. Higher the Ka value, stronger will be the acid. That is Ka. And we also know that there is another term called as pKa. What is pKa? Negative log of Ka. Negative log of Ka is pKa. And you know that Ka and pKa are inverse. They are inverse related. And you should remember that pKa values, pKa values, how they are related to acidic strength. Lower the pKa values, I am writing here one statement. Lower the pKa values, stronger will be the acid. Lower the pKa values, stronger will be the acids. Okay. Like that, based on pK, we categorize the acids. pK. If pKa value is less than 1, if it is less than 1, okay, it is strong acid. It is strong acid. If the pKa value, if pKa is from 1 to 5, is between this, then it is moderate acid. It is moderate acid. It is if the pKa is 5 to 15, 5 to 15, it is weak acid. It is weak acid. And if pKa value is more than 15, if it is more than 15, then it is extremely weak acid. It is extremely weak acid. So based on pKa, we have classified this. So basically what is here? Carboxylic acids, when they dissolve in the water, they produces the respective carboxylate ions and OH minus ions. How do you represent their concentrations as Ks or pKs? So higher the pKa value, lesser the acidic strength. Lower the pKa value, stronger will be the acidic strength. So that is about acidic character, pKa and Ka. Okay, next. Next, carboxylic acids are more acidic than alcohols and simple phenols. Alcohols and simple phenols. Okay, due to greater stability of carboxylate ions. Okay, that is, you can see the resonance in carboxylate. This is a carboxylate ion, right? What happens in this? If the negative charge is shifting like this, 5 electrons shifting upwards, right? So I will write R CO minus double bond O, right? Now the resonance angle of these two, I would like to write like this: R C O and O with partial double bonded characters and negative charge. This is resonance stabilized. Resonance stabilized carboxylate. Okay. So due to greater stability of carboxylate ion, carboxylic acids are more acidic than the alcohols and even simple phenols also. So even though resonance in phenols is more than compared to the carboxylic acids, but due to the charge distribution is on more electronegative oxygen atoms, carboxylate ions are more stable than a simple phenoxide ion. That is why we are saying that carboxylic acids are more acidic than simple phenols also. And carboxylic acids strength depends on the substituents also. Means if the carboxylic acid contains electron withdrawing group, if electron withdrawing groups are present on the carboxylic acids, they stabilizes more carboxylate ion. They give more stability to carboxylate ion. So acidic nature increases. Acidic nature or acidic character increases. If electron releasing groups are present, if electron releasing or donating groups are present, then they destabilize the carboxylate ion and they decrease the acidic nature of the carboxylic acids. Okay, so there are certain effects of the substituent group present on the carboxylic acid. So we'll see some examples. So let us take here one example in this case. Okay, methoxy benzoic acid. Okay, normal benzoic acid, and let us take paranitro benzoic acid. Paranitro benzoic acid. Now in this, which do you think is more acidic? Here this nitro group is, you know that it is electron withdrawing group. It stabilizes the benzoate ion more. So automatically the acidic character is more for paranitro benzoic acid than compared to the normal benzoic acid, then compared to paramethoxy benzoic acid. Why? Because this methoxy group, as you know, it is electron releasing group. It destabilizes, electron releasing group it is. It destabilizes the carboxylate ion. That's why it is less acidic. It is less acidic compared to benzoic acid. Okay. So if electron withdrawing groups are there, they increase the stability of the carboxylate ion such that acidic character increases. If electron withdrawing groups are there, they increases the stability of carboxylate ion, acidic nature increases. If electron releasing groups are there, then they decreases the stability of carboxylate ion, due to which acidic nature also decreases. Example, paranitro benzoic acid is more acidic than paramethoxy benzoic acid. Okay, so still more examples will continue in the next class.